So, a very good afternoon to everyone. So, am I audible?
Yeah, yes, you are.
Okay, thanks. So, we will be starting in 5 minutes. We'll wait for 5 minutes for another students to join, then we will start.
Okay. So actually, Rohit, I had mailed you regarding the PDF material.
Yeah,
You
yeah, yeah. Actually, I am gathering like all the PDFs and merging. I'm trying to merge it in
okay,
one.
okay.
Yeah. Okay, so a very good afternoon to everyone. So, is my slides visible to everyone? Can anyone confirm?
Yes, Rohit.
Okay, okay, thanks. Okay, so today we will be solving some numericals, majorly some numericals of the mold filling. And before that, I will be briefly uh, recapitulating your terminology, this casting terminology, and briefly derive the top gate and bottom gate feelings derivations from. So if we see like the casting terminology, things on okay. So if we see the basic casting terminology, we can see like the major parts are like the pouring basin, riser, runner, mold, then the cope and drag, the parting line. These you have already been these are already being covered in the theory by Professor Jha. I think someone again. Okay, so the majorly the purpose of the gating system is to permit complete filling of the mold cavity and the minimum turbulence so as to minimize the gas pickup and to prevent unwanted material from entering mold cavity. These have already been covered in the theory part. So I'm just briefly summarize. So as you can see in this figure, generally the molten melt is poured in the pouring basin, and further it comes from the sprue, and then later on there is a provision of the sprue base, and which help dissipating the kinetic energy of the falling stream of the molten metal. After that, it goes through the runner and then followed by uh, and there is also provision of the choke, which is usually here, which helps trapping impurities such as dross or eroded sand, and thus prevents them from going into the mold cavity. Okay. And then then if you see there is there is a provision of riser, which is generally a hole cut in the coop to allow the molten metal to rise above the highest point in the casting. So so these have already been covered, so I'm not usually focusing on these. Now, like if we come to the top gating and the bottom gating, uh, the derivation of uh, these part, like the filling time, like how much time it will be requiring for the filling. These have already been covered also, but I will be briefly summarizing how these can be derived. So firstly, if we talk about the top gating system or the vertical gating system, we can derive the filling time of the mold by simply applying the Bernoulli equation between point 1 and 3. Firstly, I'm believing that everyone has watched the videos of the week 2, week 3, and week 4, and then they are like they have the basic knowledge like what are these what is the sprue and what is this mold and all. Then only so I'm assuming that everyone has watched. Okay. So now if we apply the Bernoulli equation between point 1 and point 3, simply for deriving the formula of the top gating, once. Okay. So we can see so if we so we simply can write it as h1 plus p1 by rho g. plus v1 square by 2g. I'm assuming that there is no frictional losses and all. Then if I am equating it to like at point 3, I'm simply writing as x3 plus v3 by rho g plus v3 square by 2. So like generally the top gating system is at the atmospheric pressure itself. So these pressure terms will be equated like as they are atmospheric pressure. So they like from the left LHS and RHS they will get equated as P1 is equal to P3 equal to atmospheric pressure. It is uh, written here also. And then the velocity at the point 1 can be approximated as 0. And then if we equate like these these two terms like then we can get like then we will get the like I'm directly skipping one step like, so if we from this here we can like we can get a term for v3 like velocity at the point 3, and then by applying the continuity equation we will get as and then we can find out the filling time by simply as this has already been covered. That's why I am like going a bit fast because the major focus is on the solving the problems of this tutorial. That's why. So from here, like we can find out the filling time as volume of the mold divided by this area of the gating system and the velocity at the gate entrance. This is for the top gating system. Now, if you see for the bottom gating system, then we again need to like apply this Bernoulli equation, and then we will get that like the velocity at the gating system. This is for the top, and here like I'm writing for the bottom gating system. So here at the velocity at the gate, which is like v3. Here I think everyone is with me and they can get because they have already watched the theory part. Now the velocity at the gate, which is the velocity at the point 3, which can directly be like written as I'm skipping the step of writing the Bernoulli equation and all. So generally, so majorly for the bottom gating system, we need to apply the Bernoulli equation between point 1 and 3, which is this, and then point 3 and point 4. So we will get this as ht minus s. This will be the like first equation we will get, and then we will assume that as the molten melt is entering into the mold, so the height ht will if it moves like by distance of dh in dt time, then we can write it as like area of the mold times dh. We can equate it as area of the gate, then the velocity of the gate times dt. And then from these two equations we can like we can substitute it and then integrate in terms of the filling time for the bottom gate, and we can easily get the filling time for the bottom gate. So in today's tutorial, like majorly I will be covering for the top gating system, and in the next tutorial we will be covering the numericals of the I will be covering the numericals of the uh, mold different code design, pattern design. So So today, the first numerical is, so I will be solving the first numerical for your understanding, and later on from second, third, and fourth, you all can like try with me. I will be giving like some time, and then we will discuss uh, these are very not very tough to grasp. But so firstly, the first numerical is there is a mold cavity of 1200 centimeter cube volume, which has to be filled through a sprue of 10 centimeter length, feeding a horizontal runner. The cross-sectional area at the base of the sprue is 2 centimeters square. You can take G as 9.81 meter per second square, and you can neglect the frictional losses due to the molten melt flow. And we need to calculate the time to fill the mold cavity in seconds. So okay, so if firstly if we draw it, this is the sprue. From here it will be entering into a cavity which whose volume, the volume is 1200 centimeter cube. And then this area of the area and the area at the base of the sprue is given as 2 centimeters square. uh, and the mold cavity of 1200 volume has to be filled through a sprue of 10 centimeter cube, the 10 centimeter length. And this length is 10 centimeter. So we need to calculate the time to fill this mold cavity. So this area of the sprue, as it is not given, so we can take it as the area of the sprue as the area of the gating system also. So it can be written as area of the gate, which is 2 centimeters square, and then we need to calculate the T filling time. So as we have uh, so as you just saw uh, this is a top gating system. As the parting line, if we see, we are filling below the parting line. So we need to calculate the filling time for this mold cavity. So as we just saw, we can write a Bernoulli equation for this between point. We can write here between point one. If we give it point two and point three. So just like this, we can write a Bernoulli equation between point one and point three. So we will directly use this the final output of for the stop gating system, which is the T filling is equal to the volume of the mold cavity divided by the area of the gate, and then multiplying by the velocity at the gating entrance. So if we write it as T filling, we can write it as the volume of this cavity, which is 1200 centimeter cube, divided by the area of the gating system, which is 2 centimeters square. Then it is multiplying by the velocity at this gate. So the velocity, when we will I'm skipping the step of writing the Bernoulli equation. So here it will come as directly as v is equal to root 2 gh. So I'm writing it as directly as 2 multiplying by g in the coordinate is given take as 9.81. I'm taking it as 981. If I'm taking it in centimeter per second square, and then multiplying by the height is given as 10. So here from here we can so if anyone will solve, he or she will get the T filling time as around 4.2 seconds. So I will request all of you to please try this question. It is same as previous, but only the dimension you need to take from the take from this figure. That's only the difference. So I would request everyone to please try the question number 2.
Excuse me, sir.
Yes, sir.
So previous problem, while we are
Yeah.
find outing the velocity at point 3,
Point. Yeah.
root 2gh, that is
Yeah.
g equal to 9.81,
Yes, sir. Meter per second
that
as
is
well.
in
Yeah.
meter.
Yes. So
You are not you are not converted into centimeter.
yeah, I wrote it as I'm taking it as 981 centimeter per second.
981.
Yeah, 981. Yeah.
So 981 centimeter per
Second square.
second square.
Right, right.
Okay.
Yes.
981 centimeter per second square. Then while we are calculating this, we are getting this flow time is 4.2 seconds.
Yes, sir. Right.
Yeah, it's okay.
Okay. Thank you. Shall request everyone to please try this problem number 2.
So it's Rohit. That's like we have to multiply and 40 times, 15 times, 30. That is the casting dimension. That is the volume.
Yeah.
Divide by root 2gh into what else we have to multiply?
Are you asking for this problem number 2 or problem 1?
Two problem two,
Okay.
the
Okay.
which is the displayed one. So
Okay.
is it in the denominator I'm asking? So in the root 2gh, 2 into 981 into 20, right?
Yeah. Right. Right.
Multiplied by the pi by 4 d square, that is
Yeah.
pi
Right.
by,
Yeah.
that's
Yeah.
that
Right.
that's right, right?
Right. 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 That's right.
Okay, okay, okay.
Yeah.
So is it 28.93 seconds?
Yeah, it's the right answer. Yeah. So anyone who has also like got the answer?
So 28.93 seconds square.
Yeah, yeah. 90 seconds. Yeah,
Yeah.
yeah. Right. So, so I will like briefly write like how it's solved. So like so we need to write the Bernoulli equation between the point 1 and 3. And as the pressure is the atmospheric pressure, like so I'm ignoring the term, the P atmospheric term. So I am writing it as like so it will be like V1 square by 2G plus height I'm writing as Z1, and I'm equating it as like point 0.3 V3 square by 2G plus Z as I'm taking it as datum as 0 because I'm writing it as 0. Okay. So like I can neglect V1 around 0. So then so finally I will get like V3 as root 2GZ. So which I can calculate as 2 times 981. Then I will multiply it by 20 as that is like 20. The filling height is 20 centimeter. So if I calculate, I will get V3 as so I will get some V3 in centimeter per second. Then I will apply the continuity equation. So so I'm writing it as like oh sorry. So I will be writing the continuity equation, and as I need to fill this volume, which is dimension as 30 centimeter, 15 centimeter, and then 40 centimeter. I can calculate the volume as it is the volume will be LBH, so it will be 30 multiplying by 15 by multiplying by 40, and then I can like write as directly I'm writing as the continue by the application of the continuity equation. I will get the T filling time as the this volume of this mold, which is like 15 times 30 times 40, and then it will be divided by uh, uh, sorry this this V3 which I have calculated, and then multiplying by this area which and the diameter is given as 2 centimeter. So finally I will get like the answer is 28.92 seconds, 92 or 93 around this. Okay. So so this is the like third numericals. I request everyone to please try this. So I will read the question for you all. Like so, there is a sprue in a sand mold has a top diameter of 20 mm and a height of 200 mm. The velocity of the molten metal at the entry of the sprue is 0.5 meter per second. And assume acceleration due to gravity as 9.8 meter per second square and neglect all the losses. If the mold is well ventilated, the velocity of the molten metal at the bottom of the sprue is so so generally if we able to see what if we able to draw it in a proper schematic manner, the problem is very simple.
Is it 2.5 meter per second?
2.5 meter per second, no, no, it is coming around 2 meter per second. Can you tell how you try to go through this problem?
No, it's actually based on the continuity equation. It's A1 V1 equal to A2 V2.
Okay,
So A1 I considered it as pi by 4 d square. That is on the top there is 20 diameter given,
okay,
and first velocity is zero point 0.5 meter per second,
okay,
and the second area is not given, and
okay,
velocity we are able to calculate using root 2 gs, that is 2 into 9.81 into 200.
okay.
So if you solve this thing,
So okay, okay. So 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 I will be solving it. Okay. Uh, so if we draw the diagram, I am writing the terminology as 1, 2, and 3. So it is given that a sprue in a sand mold has a top diameter of 20 mm. So the top diameter, which is for 2, which is I'm writing it as D2 is 20 mm, and a height of 200 mm. So this height, I'm writing it as a sprue height as 200 mm. And then the velocity of the molten metal at the entry of the sprue is 0.5 meter per second. Okay. So entry of the sprue is this is the sprue. So it is given as U2, which is the entry of the sprue as 0.5. Assume acceleration due to gravity is 9.8 meter per second square and neglect all the losses. If the mold is well ventilated, the velocity of the molten metal at the bottom of the sprue is okay. So from this this is 200 and this we don't know. So I'm writing it as total height HT, which will be the sum of the edges. This is 200. Okay. So I will be calculating this. I'm writing it as HC. So I will first calculate this at C. So I can write U2 as root 2G. Let's see. If I will apply Bernoulli equation, I will get this. And then here U2 I have been given as like 0.5. So if I will calculate it, I will be getting HC as 0.5 square divided by 2 times 9.81. So I will, if I will 0.5 HC, okay, velocity, okay, so it is in meter itself, okay. So from here, like I will be getting HC as 0.01274 meter. Further, I will be like as I need to calculate the velocity at u3, so I will be writing Bernoulli equation between zero point 0.1 and 0.3, and again the assumptions are same, like the pressure is like I will be taking as atmospheric pressure, and then I will be equating V1 as 0. Sorry. So from here, like I will be getting the total height as 200 plus I will convert it to mm, or the unit will be the same. I will convert it in meter, and then I can like easily calculate this velocity at 3 as this total height. So from here I can I will be getting this u3 as around around 2.04 meter per second. Yeah. So these are the assumptions that it has already been given, like firstly like v1 I need to take around approximately 0, and the second is the p1 p like it is happening at around atmospheric pressure. So this is how the it will be solved. And then to like so if you will be like solving for the comprehensive exam, uh, or like if you will be solving it for the comprehensive exam, you need to like specify all the assumptions you have made, and all the assumption at each point, and like you can't like directly jump into these two equations, so you need to like directly write the Bernoulli equation between point 1 and 2 or point 1 and 3, and then you need to calculate how these velocities are calculated. So like now we will be moving to the problem number 4. So I will read it for you. So it is given that like 200 mm long down sprue. This is the 200 mm. Sorry. So this is like 200 mm long down sprue, which has a cross sectional area of 650 mm square. So this is the cross sectional area of 650 mm square, like where the pouring basin meets the down sprue. That is at the beginning of the down sprue. A constant head of molten metal is maintained by the pouring basin. The molten metal flow rate is 6.5 multiplying by 10 to the power 5 mm³ per second. Considering the end of the down sprue to be open to the atmosphere. So again the assumption is same, like we need to take P. So again both sides, if you will write the Bernoulli equation, P atmospheric will be cancelling out. And the acceleration due to gravity is 10 to the power 4 mm per second square. The area of the down sprue in mm square at its end, avoiding aspiration effect should be. So please try this. It is also the same problem. It's only not much like only like the recapitulation of like the application of the Bernoulli and all.
Rohit,
Anyway,
can you just go to the previous slide once?
question number 3. Okay.
Yes.
Yeah, sure. Yeah.
Okay, you switch to the next slide.
Okay, okay, sure. So please try this trick, this numerical.
Area at the bottom 325 millimeter square.
Sorry, can you please repeat? Like,
Area at the
okay,
bottom of the
okay,
sprue is 325 millimeter square.
okay. So like, can you please tell us the procedure, like how you proceeded? Because
Flow rate it is given 6.5 into 10 power 5 millimeter cube per second.
right, right.
That is equal to area at the gate and area at the gate at the bottom, area at the sprue at the bottom and velocity at the sprue V3.
Okay.
Okay.
Yep.
So V3 is equal to square root of 2g h. H is given. G is also given. Find out velocity at the bottom of the screw.
Okay.
Then area equal to 325 millimeter square.
Okay. I think so there is some calculation mistake because the answer is like 290 millimeter square, square. So I will be doing it step by step, so others may also catch up, like who are not with me. Okay. So right, like the molten metal flow rate is like 6.5. So like if I divide it as I write it as V1 and then here I write it V2, writing it as 1 and 2. Okay. So this height is I have given in the constant is given as 200 mm. So and the melt flow rate is 6.5 into 10 to the power 5 mm cube per second. Okay. So I can write as like the Q, which is given as 6.5 into 10 to the power 5. This will be equal to the area and then the velocity, and then the area is given as 650 mm square, and I will be writing it as velocity. This will velocity is at the point 1 v1. So I will be I will get the v1 as directly as 1000 mm per second. Then I will be writing the Bernoulli equation again. So I'm avoiding the pressure term. Then I will be writing as h1 plus v1 square by, this is square not cube, v1 square by 2g plus v2 square by 2g. And then I can write as h is given as 200 plus v1 I have calculated as 1000 by 2 into g is 10 to the power 4. It is given to take in the question as non 9.81. So I will be equating it as v2 square by 2g. So again 2 into 10 to the power 4. So if I will solve this, I will get v2 as around 2236 mm per second. Then I will be solving for this A2, area of the down screw at the end. So again I can write A2 as this volume I have already been given 6.5. I will be writing as 6.5 times 10 to the power 5 divided by velocity I have calculated as 2236. So if I calculate then I will be getting as V2 as 290.7 around or 8 around mm square. So anyone who has any doubt in this till now?
So during this Bernoulli's equation,
Yeah,
h1 h plus v1 square divided by 2g
yeah,
plus V2 square divided by 2G.
Oh, sorry, it is equal. Oh, sorry.
That is.
Yeah.
Okay.
There. Uh, Okay then, so then we will move to the question number 5. So this is the easiest of the all this all the problems till now. So the question it is given like in a sand casting process, a sprue of 10 base dia and 250 height leads to a runner which fills a cubical mold cavity of 100 size. Calculate the volume flow rate in cube per second.
So is it 0.4?
Can you please tell me the unit?
A meter per second?
No, it is not 0.4. So I think so it is you need to directly calculate the flow rate as uh, velocity at the sprue and then the area. So velocity you can directly calculate as root 2 times G will be like 9.81. H is like 250, and then if you like take the unit equal, then the 10 to the power 3 will come, and then you need to multiplying it by pi by 4, then dia is given as 10 square. So by solving this, like you will get as the around this. So firstly, like if it will be the final exam will be like the filling the only the like the options won't be given like the practice made by the gate. So if it is like filling type, like so you need to like carefully see like if you are not making a mistake in calculation. So if it like you need to see like each and every point of the question, like it is given that the unit is calculated in mm cube per second, and if you wrongly mistaken, then you will get 0 marks. So I added only to like I added this question only to like clarify that we need to see the units very carefully. So in which like the answer is asked, or like how will it, so this problem is very simple, but majorly like students do mistake in like calculation, because they calculated in wrong units and then they get negative of 0 marks. Okay, then so please like move to the question 6. So here it is given like in the sand casting of the hollow part of the cylindrical core of dia
Sir,
120.
previous sum, please.
Yes, yes, yeah.
So 250 into 10 power 3, which you have taken, it is converting millimeter to meters, is it?
It is
So
wrong. 10 power minus 3.
I'm like writing it is
It is,
like
it is
9.
already in millimeter. 250 it is
Yeah,
already in millimeter.
yeah. I'm not converting 250. I'm writing is like 9.81. I'm converting in mm per second.
Okay.
That's right. Yeah,
So that is in
meter
meter
per
per
second.
second,
Yeah,
meter per
yeah,
second square.
yeah.
That you are converting it into
Two.
millimeter.
Yeah, right.
Okay. 1739.42 millimeter cube per second.
Yeah, right. 1793. It is not point. 17394 point something. It will come.
Oh,
Okay.
no, not point.
Yeah.
Uh,
Okay.
no, actually, Rohit, it is 2 into 9.81, right? So you have taken 9.81 only, right?
Yeah, but I like I wrote the converting factor here for 9.81.
Oh, okay. So that converting factor is not for 250, it is for
250. Yeah, it is.
9.81.
Yeah. As I need to calculate it in mm cube per second, so I need to convert everything in mm. That's why. Okay.
So we can directly take it as 981.
981. It will be in centimeter per second, na? Then you need to convert the centimeter to mm.
Oh, okay, got it. Okay.
Okay. So I think like it is
So,
clear
so,
now.
so this is
Yeah.
so this is 98.1 which you have taken now.
Sorry, it will be if you will write it in mm, you will get 9810. You need to like multiplying it by 1000, like
Yeah.
9.8.
Okay.
Okay, sir.
Okay, thank you.
Okay.
Yeah. So like now we will move to like question 6. So it is like in the sand casting of the hollow part of the lead, cylindrical core of dia 120 mm and the height 180 mm is placed inside the mold cavity. The densities of the core material and the lead are like I think I have written something. is the core material, and this is liquid metal basically. Yeah. So it is the filling. Okay. Core metal and lead are 1600 kg per meter cube and 11,300 kg per meter cube. And we need to calculate the net force that tends to lift the core during the pouring of the molten metal. So this was covered in the week 3 in the theoretical part by Professor Jha. So in the core design section. So if you will see there are the density of the core material and then the density of the, this is basically the some typo error, so it will be the density of some liquid metal. So I'm okay, so the lead is being filled, not a typo error. So whenever we need to design uh, the core, so they generally there will be the net upward force will be due to the difference between these two. So the first one is the core material density is given, and then the material which is being filled whose density is given. So there will be a net upward force will be due to the, so this F net, if you will balance the force equation, then F net force on the core, it will be equal to the density of the material which is being filled, which is 11,300, and then difference of the density of this core material multiplying by the gravitational acceleration times speed volume of the material which is being filled. So this is directly we got, if we apply the force balance, this we will directly get, and it is already been taught in the class also. So if we see here and here V is the volume of the core. D is the gravitational acceleration, and then this rho is the density of the liquid metal. And then this sigma is the density of the core. Okay, so please calculate it and tell the final answer which you will be getting.
So what is this F net formula? It is the difference in two densities multiplied by gravitational force and then volume.
Yeah. So if you will see if you will see the theoretical part clearly, how the Professor Jha explained. So if you there will be on the core material there will be two forces will be acting. Okay. One will be due to the this liquid metal poured. So if you say F1 here and then F2 here, these two metal force, we need to calculate the F net force. So this is suppose the F net force, then we can directly calculate the difference between these two forces. And the first force is due to the you can directly write F1 is equal to m into g, which is mass times the gravitational acceleration, and mass you can write in terms of rho into v, volume in terms of density of the as and then you will from here f you will be getting as f1 minus f2. And then you can you can dot it in terms of m into g and then mass in terms of some density, and then this another force will be again in terms of this. So then you can take common and then find this f net on the core. So the more you will be like the theoretical part, you can again go through that theoretical part to see like more properly like what Professor Jha is like teaching, and then you can again come back to this question and then see, and you will the concept will be more clear to you. And okay, so like try to solve it.
ग्रुप पे देना दीजिए ये नेक्स्ट हाँ अच्छा का वही जाएगा
So if you like if you calculate the volume as
193.61 Newton.
yeah, right, that will be the answer. So if you will calculating the volume as 5 by 4 by dia is 120 mm, then the height is 180 mm. So the volume you will calculate by this, and then you will directly write this F net as 11300 minus 1600 times the volume which will be you will be getting. So this F net will be like around 193 approximately 193 Newton. Okay, so let's move to the seventh question. So here it is like given like in a slush casting process. So the it is covered in the week 3 is like special casting processes, or some another or in some another lecture of the week 3. So this is a problem based on this. So it is given like in a slush casting process, a casting of thickness 5 mm is formed when the mold is inverted after 100 seconds, and a thickness of 7 mm is formed when the mold is inverted after 200 seconds. What is the time after which the mold has to be inverted to produce the thickness of a casting is 2 mm? So like if you will see like the if you see the slush casting, so generally the thickness is proportional to the point 0.5 power like solidification time to the power like root of the solidification time. So this is the slush casting, and it is generally used for making the thin coatings, hollow thin castings, hollow statues, toys, decorative items, etc. And then the thickness of the casting is given by this formula for that particular casting, for that particular slush casting process. So you directly only need to like make two empirical equations like thickness 1 will be like equal to, if you will like remove the proportionality constant, then you will get the thickness T1 as C1 times Ts to the power 0.5 plus C2, and then same for the T2. Then you need to calculate then you need to like calculate these two constants C1 and C2, and then do it for the, and then calculate the thickness 3 T3 for the given like for 2 mm thickness casting. So please try this, then we will discuss this more. So I have also like prepared like brief like a short note like 2-page short note regarding all the special casting processes, and in like one or two like in maximum to 4 to 5 lines. So this will be like helpful to revise all these casting processes which were covered by the week 3 by Professor Jha. So I will be sharing this also in this PPT, and you will get the link also. It will be good for you to revise like easily, like if you have like if you have seen the lecture carefully, then it will be good to revise in it will help you to revise for the final exams. So if you will write it as like the casting of the thickness, so if you take it as T1, so I'm using the notation small t as for the thickness and capital T as the solidification time. So if you will write as like uh, so in the question it is given as T1 as like 5 mm, and then the respective corresponding the solidification time is 100 seconds for that. And then similarly 42 it is 700, and then the corresponding solidification time is 200 seconds for that. And it is being asked for like 2 mm. What will be the T3 or the solidification time? So this is the question. Okay, so now we are given the relation as between the thickness and then the solidification time. This is usually the case for the plus casting process. Okay, so we can remove the proportionality sign, and then we can write in generalized form as T is equal to C1 some constant times solidification time plus C2. So we will get two equations from that, 1 and 2, and we will calculate C1 and C2. After calculating C1 and C2, one variable like T is given, then we will need to calculate T3 from this. Okay, so try to solve this now.
What is C1 here? Like, what value should we take?
Look, these are the constant after removing the proportionality sign from this relation, small t, and these are the constant you will calculate from these two. So you will write so you will need to make equation like 5 is equal to C1 times root 10, or sorry, it is 100 plus C2. Then similarly for second equation, C1 you will write as 7 is equal to C1 times root 200 plus C2. From here you will calculate the C1 and C2, and then you will calculate T3 by putting it back in this equation. Now you have C1 and C2 values, so you can calculate it. Okay. Okay, then so by solving you will be getting C1 as like 0.48, and then C2 as 0.17. Then you need to put it back in this relation. Then from that you will get like the T3. So you will get the relation as T as equal to this times T1 plus 0.17 as C2. Now you will put the T3 values here, like this 2 mm, which is equal to 0.48 times we need to calculate T3 plus 0.17 something. From here can you okay, so from here we will be getting T3 as around 6.2 seconds. Okay, so these are the few of the numericals which I covered, and then in the next week we will be discussing more about the next week I will be trying to cover at least like more than 7 problems. It will be because next week will be a lengthy one because it will be covering pattern making, mold making. It has like uh, lot of numericals to cover in that in the next week, the week 4 and week 5 combinedly. So who is trying to join? Okay. So before that, I have summarized like some of the points like which we were discussed by Professor Jha. Like if you talk about the like I have make an 2-page notes for all the solidifications, for all the casting processes. Like uh, like I have written say I will dictate for the like die casting, and then for another I will be sharing the notes only. So you can go through that and to clarify the doubts and all. Like for the die casting, I have summarized it in points like it provides complex shapes within closed tolerance. And second point, these are produced at high rate of production. No machining is required in brackets. Third point is these are much stronger than plastic injection molding, produced with thinner walls. These are durable and dimensionally stable parts. It can produce like thousands of identical casting within specific tolerance. And the die has two parts. Then the stationary part, which is like covered by die, and then the second is the movable part, which is ejector die. These are generally made of hot work steels or chrome vanadium or chrome steel. Okay. These and the walls as thin as 0.38 mm can be die cast using external pressure. It's a net shape or net shape forming process, and I summarize the benefits and another defects of that. Like the defects are generally that the die life decreases as the melt temperature is high or limited to non-ferrous alloy, and then the products may have porosity, like air is entrapped sometimes. And then the benefits are thin section with complex shape is possible, precision manufacturing with close dimensional tolerance, true shape as of die cavity, casting details are reproduced with high degree of precision, and the sound casting and less defective and less cost. So I have summarized this for all the majorly covering all the major important processes. Like this will be helpful for your revision, but you need to first go through the weekly lectures clearly. If you won't go, then you won't understand. Like because these are only the bullet points or like the
Rohit,
short.
actually, you are telling that week three they have covered all this thickness and all types of casting and everything, but I don't think so. It is covered in the week three. It may be covered in the further weeks lectures, but in week three it was more about organic binders and
Yeah, yeah. This
molding
question,
process, mold
yeah,
making, all these things.
yeah. This slush casting process, like the theory has been covered, uh, but this has not been covered, right? But as I have already written, like this is the thickness, this is the relation. So if question will come like this is the basic mathematics. I think we can solve it because the relation has already been given. So any type of relation, like for one particular casting process, can be made like this to relate these to have this kind of relation and all. So that's why I added this simple question here. So, but I think the others were covered in the or the
Yeah,
other.
yeah, yeah. All this sprue technology, riser design, and all this were covered in week four.
Okay.
The problems which you solved in the beginning, but I'm talking about this solidification time is directly proportional to
Yeah, yeah,
thickness.
yeah, right, right.
This
So,
problem.
okay. Actually, why I covered this is in week 3 because week 4, like, we need to cover a lot of things because it has design because more of the more these like it covers a lot of numericals. So some part of that I covered in this week because everything will be won't be able to I won't be able to cover in week 4 itself. So that's why I tried to sum up some of the questions from week 4 and week 3 because week 3 was majorly the theoretical part which I have already like summarized in 2 pages for you, so you can go through that.
Okay, okay.
Okay. So Okay, then so any other queries or any other
Is
like
this
student?
2-page write-up you are given, sir? Where it is?
So I will be sharing the link. So and then sharing the link on. Actually, they are like NPTEL team is asking us for like we upload it daily on our YouTube channel. There is a YouTube channel where the all the videos are being uploaded, and then the slides are also these slides are also present there. Then you can like download the slide and this 2-page write-up. I will be adding in this PPT after like 11 and 12 number page, and then I will upload it, so you can like go through and then revise it.
Okay, sir.
Okay, thank you. Yeah. So any other like queries if you have, then or else we will like end this week's, and then week 4 will it will be extensive and it may go more than 2 hours because it has like many numericals and I need to cover a lot of things. That's why.
Okay, sir. Thank you, sir.
Yeah. So any other student who has any doubts like, or anything we want to say, reviews or anything?
So during this lecture period, that professor has given PPT.
Yeah.
It is only first topic. First slide is in the topic. Second slide is title. Third slide is thank you.
Okay.
Only it is like that only. Previously, while I was doing some other courses in NPTEL,
Okay.
whatever the lecturers are given, it was all there in the PPT itself. While we are
Okay.
missing the lecture, we can while we are going this PPT, then we can easily understand and attend the exam. But in this this program, and that only I can see only 3 slides. First one is the
Okay.
introduction, second one is the topic, third
Okay.
one is you.
So I think like there is some like error in the uploading while they are uploading. So you like if you will go to the lectures, there will be like video transcript also is written. So each line is Professor Jha is written there. So
Video transcriptions, it is the formulas and all is not at all
okay,
there in the
yeah.
transcription.
Okay, I got it. Yeah. So
So
I
that is
think
a problem I am facing from the beginning itself.
okay. So
Please, can you make something arrangement to provide this PPT?
okay, I will mail them. Like you can also mail them regarding the support team and all. So they will look it and then they will try to like re-upload or I think whatever they will do. So you can write a mail to them. Okay. So that's how like these things will be highlighted to them.
To which mail I had to send?
If you will go to the NPTEL site, they will be like, and then to the helpline, there will be some mail ID will be might be provided there.
Okay.
Okay.
Okay, right.
Okay. Then, thank you everyone. Then we will be. Yeah, Sanjay, you want to say something?
No, that's all. Yeah.
Okay. Thank you then everyone. Like we will be connecting again next week the same time, and then we will cover more numericals and then more doubts we will be covering. Okay.
Okay,
Hope to
okay,
hope
thank you.
hope hope to see you all again. Okay. Thank you.